Max. So if you have a question that you haven't been able to ask via email or however, you're welcome to ask. But you should actually be asking questions during office hours and or by email. So, any questions? Yes?
Is the quiz at the end of class?
There will be a quiz at the end of the class, at the end of the second hour. That's usually when I give it, just in case some people are late. And that way they won't miss the quiz. Anything else? Okay. Today we will start the material of this course in earnest, and we will be looking at failure theories. But before that, your book goes through a discussion of stress concentration, so I'd like to go over that first and show you what it is, how we use it, when we use it, when we don't use it, and why. So what's stress concentration? You had some of this, at least, during your studies of 218 and 219 materials. What's the definition of stress concentration? Did you have stress concentration in 218 and 219? Do you remember whether you had stress concentration in 218 or 219? Got to answer a question somewhere along the line.
I don't remember.
You don't remember? It's honest enough. Anybody else? Do you remember talking about stress concentration?
Isn't it an abrupt change in stresses?
Isn't it what?
An abrupt change where stresses change?
Not necessarily abrupt. It doesn't have to be abrupt. But it is a change, yes.
Yeah.
But it doesn't have to be abrupt. Stress concentration, and I'm sure you talked about it. You may not remember. If you have a plate, let's say, with a hole in it, and you have loads applied like that to the plate, and you want to calculate the stresses, okay? What we call nominal stresses, or P over A. Let's say in this section, what you do is you take a free body diagram, call this force P, you say there must be a reaction here equal to and opposite to that, and if this cross-sectional area is A, the nominal stress is defined as P over A. And this stress is assumed to be constant over the entire cross-section. Similarly, if you want to calculate the stress here, then you take your section here, this would be section 1, then section 2, we'll call this A1, A2. In section 2, we have sigma 2 equals P divided by A2. Clearly, A2 is smaller than A1. Everybody okay with that? Therefore, sigma 2 is larger than sigma 1. And as a nominal stress, it's still assumed to be uniform across the cross-section. But when we take a look at some tests, the fact that it's uniform across the cross-section is not borne out by tests. By tests, I mean we put a strain gauge here, and then a little bit further away from this hole, and we measure strains, and we find that these strains are not the same. They are different. They are larger near the hole, in this case, and smaller away from the hole. So although the average stress is still P over A, the distribution is different. So if we take a look at the distribution of those stresses, we'll find something like this. The same thing on the other side, of course. There is an increase of stress near the hole, and its value drops off to the nominal stress when you get further away from the hole, very quickly, usually. So whenever there is a discontinuity in the cross-section, so it could be like this, could be like that, there is stress concentration here. Whenever there is a discontinuity, the stress at the discontinuity will be magnified. This phenomenon is called stress concentration. The magnitude of the stress that is magnified is found by multiplying the nominal stress by what is called stress concentration factor. K sub T is defined as the maximum stress divided by the nominal stress. Sigma O is called the nominal stress. Similar to what we have found here. Both of these are nominal stresses. This stress concentration factor depends on the size and shape of the discontinuity, sometimes called flaw. For example, a different discontinuity that I can draw bigger and you can identify with is something like this. Let's say a crack. If we look at this crack under the microscope, this is what we see. The stress concentration factor for this discontinuity is dependent on two of the dimensions of this flaw. One is this length, L, and the other one is this tip radius, R. The larger the flaw, or the smaller the tip radius, the larger the stress concentration factor. So it's directly proportional, or directly related, not necessarily proportional, directly related to the length of the flaw, and inversely related to the radius of the flaw tip. So in this case, for example, the radius of the flaw is just the radius of the hole, a larger value. In this case, the radius of the flaw is the radius at the tip of the crack, a very small value. So we say stress concentration here much larger than it is there. So that's the concept of stress concentration. The way we measure stress concentration is by, as I said before, by putting strain gauges close to the floor, and of course away from the floor, and then comparing the strains and or the stress. So long as the material is acting linearly elastically, the ratio of the strains and the ratio of the stresses will be the same. Does everybody understand what I'm talking about? So long as the material is acting linearly elastically, if we double the strain, we double the stress. Agreed? Okay. So let's take a look and see how this works, since we measure strains, how it works with a stress-strain diagram, such as what you see on the screen. The solid lines, not the dashed line, not yet anyway. Let us assume that we have a case in which the stress concentration factor is 2. It could be this flow or that flow, whichever. And we apply a stress, and this is 50 KSI, so each of these is 10 KS, 10, 20, 30, 40, 50. We apply a stress that gives us a nominal value of 10 KSI. And we'll call that at point A. I don't want to use point A, not yet anyway, so I'll redraw that here. I'm going to use this point. Let's say A prime, where that's 10 KSI. This is epsilon nominal. We say, according to the top equation, the maximum stress is 2 times that. So sigma max, therefore, is 20 KSI. And of course, epsilon O is equal to epsilon max over 2. So far, so good with everybody? Is there any question? Is there anything you don't understand? If there is, please ask, because I'm going to be building on this, and it's essential that you do understand. Therefore, if we have installed the strain gauge, here, right next, I'll draw another picture here, maybe it's a little bit better. If we have installed the strain gauge very close to that flow, and one further away. You've all used strain gauges, right? In 220. If I apply a static load like that, which of these 2 strain gauges, I'll call them 1 and 2 for example, which of those 2 strain gauges will read a larger strain? 1 or 2? 1. Does everybody understand that? Right next to the hole. Of course, you can always test it, but the reason is that this point is supported on both sides by the material, and therefore it strains less. This point is only supported on one side by the material, not on the other side. There's nothing on the other side. There's a hole. And therefore, it strains more. To find the stresses, all I have to do is read the values of the strain here, go to that stress-strain diagram, read off the value of stresses. So in the example that I just gave you, when we read sigma equals 10, this is the strain. Max, that's the strain, that's 20. So we can We read the strains from the strain gauge, go to the stress strain diagram, find the stresses. So long as the material is acting linearly elastically, if the strain is doubled, so is the stress. Now let's see what happens if I look at a point such as point B. For point B, in other words, by point B I mean when I have increased the stress 3 times what it was before. I should get twice as much strain here as I get here, correct? According to what we just said. So let's say we get that. So strain here is this much, then I go twice that and go up, and I find that the stress there is equal to this value called SY. I'll explain what SY exactly stands for in just a minute. What is the value of SY from the graph? 40 KSI. What is the value of the stress at this point? Nominal stress. 30, right? So the maximum stress is 40. The nominal stress is 30. So what's the stress concentration factor? Agreed? My stress concentration factor just changed from a value of 2 to a value of 1.33. Simply because the material is not acting linearly elastically. It is yielding. And SY actually means the yield strength of the material. So we conclude, therefore, that for materials that yield, an increase of stress will lead to a decrease of the stress concentration factor. In addition, for materials that yield and strain harden, the one that I just showed you, the solid line, doesn't strain harden. You should have seen something like this in 220. You tested steel specimens, and you should have had stress strain diagrams like that. What we're looking at is that part to the left on the board. So, if the material strain hardens, what happens to it? What's the meaning of strain hardening? How many of you have taken ME315? 1, 2, 3. All of you should know what strain hardening means. It's a phenomenon by which the strength of the material increases due to plastic deformation. Now, there are reasons for it, why it increases, but not something I want to go through here. But you remember something like this, I hope. That if you load a ductile material to some point past its yield point, and then you unload it, the unloading is elastic even though the loading has some plastic parts, like that. So that's the load, that's the loading, that's unloading. Now, if someone else comes along and tests this same material, which has been loaded and unloaded, what they find as the stress strain diagram is this. The yield strength of the material, however you want to define it, and there are different definitions, will have increased. Material will get stronger. Its yield strength will increase. So, the stress concentration factor has decreased. The strength of the material has increased. So sometimes we don't even use the stress concentration factor. We say, number one, this is very localized, it's right next to this flaw. Number two, the stress concentration factor decreases. And number three, material gets stronger and therefore can resist higher stresses. So we don't use stress concentration factor. In fact, if you look at that diagram, which is called an elastoplastic diagram, the material is completely elastic to a point, then completely plastic. Look at this here. That's an increase in length with no increase in stress. The strain keeps increasing, but the stress is a constant. Doesn't increase. So, for example, if my strains that I measure via these strain gauges in this position 2 is over here, and then I take twice that, I go over there, both those stresses are equal to Sy. In reality, the stress concentration factor there is 1. In other words, it's decreased from 2 to 1.33 to 1.2 to 1.1, and therefore 1. So in this case, we don't use the stress concentration factor. There's another case in which we don't use the stress concentration factor. And that is the case in which the flaws in the material or the discontinuities in the material produce much higher stress concentration than our flaw would. Let me give you an example. I'll use this. Assume the material is cast iron. What is the structure of cast iron? It's made of what? And carbon and iron. It's not pure carbon, right? Cast iron is carbon and iron. And carbons, those of you who have taken 315, carbon is in the shape of carbon in cast iron, gray cast iron, is how? What does it look like? Anybody remember? Like flakes, like potato chips or cereal bits inside of the material. Pure carbon. So if we look at it two-dimensionally, maybe we'll see something like this. That's a flake of carbon in 2 dimensions. Now, the radius of the flaw tip here compared with the radius of the flaw tip here. This one is many, 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 many times smaller than that one. Therefore, the stress concentration factor here is much higher than it is there. So the material already has something that produces a high stress concentration. Therefore, there's no need for me to go in there and multiply stresses by 2 for that flaw, because it already has it. And when I actually look at in the case of gray cast iron, not the yield strength, but the tensile strength. When I take a look at the tensile strength of cast iron, the presence of these flaws are inherent in that strength. So, because when we test, we don't take the flaws out, we don't take the carbon flakes out, we test it like that. So those stress concentrations are already there, therefore there's no need to use that. So these are the 2 cases where we do not use stress concentration factors. And again, remember that both of these is in static loading, a loading in which there is no speed associated with the load. The increase of the load is very, very gradual. So there's no speed associated with it. There is such a thing called dynamic loading. Like if you have a beam and you drop a brick onto it, the effect of that is much more than just putting the brick on top of the beam. That's because of the dynamic effect of the load or the kinetic energy that is associated with it. So this is a little bit about stress concentration. Okay? Any questions? All right. So let's now go to the first subject of the course, the real first subject. Let's call it static failure theories. Failure theories for materials that are loaded very, very slowly, no dynamic effect. You have already used one of these failure theories. Let's say they would give you a beam like this, with a load in the middle P, beam of length L, and they would ask you, given the cross section, of course, they would ask you, what is the factor of safety with respect to yielding? You would find the point of maximum stress, either tensile or compressive, whichever. And then, how do you find the factor of safety? Factor of safety would be equal to what? Given sigma max, factor of safety with respect to yielding is equal to? Now this one you did, I know you did, so you better say something. Okay, not allowable, because allowable already has in it a factor of safety. So you say, for example, if you want a factor of safety of 2 with respect to yielding, then your allowable stress is half of the yield strength. In other words, it has the factor of safety inherent in it. But if you want to find the factor of safety with respect to yielding, say the yield strength of the material divided by the maximum stress in the material. That's your factor of safety. Factor of safety is basically the ratio by which you can increase the applied stress, applied maximum stress, before you reach a threshold stress. Threshold stress may be yielding, may be rupture, or whatever else you may want to define. In this course, S represents strength, and sigma represents stress. So when you see a SY, that means yield strength. SUT, ultimate tensile strength. SUC, ultimate compressive strength, and so on. Then the stresses are indicated by sigmas. What is the difference between stress and strength? Anyone? Well, you've got a lot of catching up to do then if you really don't know what they are. What's the stress? Go ahead.
Is stress the resistance to plastic deformation?
Is the stress what?
Resistance to plastic deformation.
Nah. How do you produce a stress? Is there stress on my feet as I'm standing here? Yes or no?
Yes.
Okay. Let's say the cross-sectional area of my 2 feet combined is 15 square inches, okay? And I weigh 150 pounds. What's the average stress?
PSI.
10 pounds per square inch, right? So in order to create a stress, you need a load. You need an area on which the load acts. Now, this could be normal stress, it could be shear stress, but you need a load and you need an area. What about strength? For example, we say this is made of steel. Let's say it's a rod. Can I say that its strength is 60 KSI? Yes or no? When you did this, you all did this, because when I wrote this, everybody said yes, 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 yes. What is SY? Where does it come from? How do we get it? Oh boy.
Through calculation.
How?
From testing.
We get it from a test. That is correct. We apply a load and get it from a test, similar to what you see or what I have on the board, and all of those can give you this. And then once that's done, once the testing is done, we say the strength of this material is 60 KSI, for example, yield strength. In order for me to say that the yield strength of this material is 60 KSI, do I need to have a load applied to it? No. If I ask you which is stronger, aluminum or steel, well, no question in your mind you say steel, right? Did we do any tests? Did we put any loads on anything? No. It's a property of the material. Strength is a property of the material. It has nothing to do with the externally applied load. Stress, on the other hand, requires an externally applied load. So one is the strength of the property of the material, the other one is produced by applied loading. Okay, so you said that this factor of safety with respect to yielding is this, okay? In other words, you defined some type of failure, in this case yielding. You said if we increase this sigma max by that factor, the material will yield. Okay? So this is one type of failure. How do you define failure in general? What is the definition of failure? You all took ME 233, right? Did you guys not use definition of failure there? I'm sorry?
Isn't the failure point at the point where, at the tip of the graph, at
The end in here, you mean? What happens there?
fracture?
The material fractures, okay? So fracture strength can be a type of failure. Yes, that's also true. Why is it a failure? Or maybe yield strength. Why is it a failure? It doesn't matter which one you talk about. The general definition is, and by the way, please read over the book before you come to class, because many of the questions that I'm asking you now, you should be able to answer. So read the book on the subject I'm going to be talking about, and a lot of these are there. Of course, they were in your previous classes as well, but maybe you don't remember. You need a refresher. So read it the night before you come to class, because otherwise, it's going to be difficult for you to understand what's going on. Yielding is a type of failure because there's permanent deformation in the material. Dimensions change permanently. Fracture is a failure in the material because of the obvious reason that once the part fractures, it can no longer carry the load. But these are not the only types of failure. Consider this. This is a flywheel, needs to rotate. And then you have a beam sitting on top of it with a load on it. If the deflection at this point is larger than the gap that is there now, then the beam and the flywheel will touch. And the beam will interfere with the function of the flywheel. The beam will have failed. It doesn't matter that the stress in it may be 1 KSI, or the strain may be very, very small. So long as it is not able to perform the function for which it was designed, the part is assumed to have failed. Now, this can come from yielding, it can come from fracture, it can come from undue deflection, permanent change of length, what have you. So failure is the inability of the material to perform the design function, period. And we are actually looking at failure, not due to deflection in this case, but actually due to undue stresses and also fracture as well. Okay, so when you did this, this is a way of representing what you did. Let us assume that we represent a two-dimensional case of the state of stress at a point. And in this case, sigma A and sigma B are the stresses at that point. Are these principal stresses? Why? Because there's no shear. That's right. There's no shear on those points. Therefore, these are principal stresses. The failure theory that you used is called the maximum normal stress theory of failure. This theory says failure occurs when the maximum stress in the material reaches that at failure, and now we define failure as yielding, rupture, or however else you want to define it, in a simple tension test. So when the maximum stress in the material reaches a critical value that we find in a simple tension test, and that critical value could be the yield strength of the material, it could be the tensile strength of the material, however you want to define it, then we say the material has failed. In this example that I gave you here, we're using the yield strength. So let us assume that here, these are both, of course, positive. Let's assume that's the case. Sigma A is greater than sigma B. So which one of these stresses reaches the critical value first? Sigma A, because as I increase the load, these will increase proportionally. If I double the load, they both double. So if sigma A is greater than sigma B now, it'll remain greater than sigma B. So failure occurs when that reaches that. So here is sigma A. We're plotting sigma A, sigma B. This is called the failure locus. And I plot a point here. Will give me the value of sigma A. Let's just give it some value, for example. 10, 5. So we plot that. And here is the yield strength of the material. The T indicates tension. As we increase the load, both of these will increase. There will come a time when the value of sigma A is no longer equal to 10, but it's equal to SYT. Then we say failure has occurred. In other words, if I increase the load, both of these stresses increase along that line. Is everybody following me? As we increase the load and keep plotting these stresses, they follow that line. If there is anything you don't understand, this is the time to tell me, because I'm going to build on this with other failure theories. This is the simplest one. That's why you've used it. It's really not the most accurate one. In fact, it's the one we very seldom use. But it is the easiest. So, what's the factor of safety? The factor of safety is the ratio by which I can increase the maximum stress before I get to SY. By what factor can I increase this before I get to this point B? Well, that factor, actually let me call it C because I'm calling that sigma B, so we won't get a confusion here. So N therefore is equal to OC over OA. And that's a graphical representation of this equation. Any questions? Okay. What if this is case 1? This is for case 1. What if sigma B is greater than sigma A is greater than 0? Case 2. Then the point, rather than being plotted here, will be plotted over here somewhere. This is case 2. And the limiting value of this comes when this line crosses what line? Yielding will occur when sigma B reaches SY, or SYT in this case, the tensor. So if I draw another line here with this as SYT, the limiting value is reached at this point, is it not? And the factor of safety in that case then Oh, actually, I need that space there, so I'm going to erase that and put it someplace else. The factor of safety will be equal to, in this case, I'll put it up in here, n equals OC prime over OA prime. Any questions? Case number 3. Sigma A is positive, sigma B is negative. One is tension, one is compression. Depending on, in this case, let us assume the magnitude of sigma A is greater than the magnitude of sigma B. Then my point plots somewhere in here. This is case 3. My load line is that. This is called the load line. This was case 2. This is case 3. Once again, factor of safety, OC double prime divided by OA double prime. Notice that this is exactly the same as that. Exactly. It's equal to SY divided by sigma max. This divided by that is the same as that divided by that. So, if you have that, we will get this line, continuation of that line. And of course, we can have another case. Oh, actually, yeah, 4. The magnitude of sigma A is less than the magnitude of sigma B. In other words, when I plot, I get this point. My load line will now look like this. And it crosses this line, which indicates yielding in compression, before it crosses that line, which is yielding in tension. So, call that A triple prime, C triple prime, and you get the idea. The factor of safety is OC triple prime divided by OA triple prime, and so on. Now we can go to the other side, say sigma B is negative, sigma A is positive, and all of that. The upshot of the whole thing is that we get an area like this. This is SYC. That's SYC, that's SYT, that's SYT. To redraw this, because I want to use it with some other failure theories as well, it looks like this. For ductile materials, yield strength in tension and compression are the same. For brittle materials, not so. Let me indicate my axes a little bit more pronounced, like this. Now, If I have a case like that, with sigma A and sigma B as principal stresses, all I need to do is plot the point. Connect from the origin to that point. If the point falls within this region, then there's safety. There's no failure. If the point falls outside of the region, the part will have failed. This is the safe area. If the point falls here, factors of safety can be found by dividing the distance from the origin to the cross-section of the load line and the strength line, divided by the distance between the origin and C, I guess I called it, the strength line. And you could be here, you could be here, you could be here, or you could be there. Any one of those. That you have already used, although not in that form, just in this form. But that's what you did. If the stress was negative, you used the compressive yield strength. If it was positive, you used the tensile yield strength, which gives you the different regions of that diagram. Any questions? Okay, let's take a break. The maximum normal stress theory, although simple to use, does not give you good results in all circumstances. So a different failure theory, that of the maximum shear stress theory, is devised. And very similar to this, it's always compared to a situation in the simple tension test. This theory, called the maximum shear stress theory, says this: failure occurs when maximum shear stress at any point in the material reaches that at yield. These are yielding failure theories. Yield, you could also say tensile, but we'll just leave it like that. At yield, reaches that at yield in a simple tension test. Now let's say a few words about why you have a theory such as this. Yielding or permanent deformation is a phenomenon in which planes of atoms slip past one another. Those of you who've taken 315 should know about that. In order for planes of atoms of the material to slip past one another and produce what is called permanent deformation, what kind of stress is required? This is what we need to do. Shear. You need a shear stress here. Does everybody understand that? So rather than basing our failure theory on a normal stress, which is not what causes slip, base it on the shear stress, which is responsible for yielding of the material. And therefore, this failure theory. Aside from that, the results that we get agree with experimental results much, much better than the maximum normal. In fact, maximum normal stress theory in some cases is dangerous to use. So let's see what situations we have. Again, sigma A and sigma B are our principal stresses. Let us assume sigma A is greater than sigma B. In this case, they're both positive. What is the maximum shear stress in the material in this case? Okay. Anytime you're asked that question, or anything even similar to it, draw more circle. And for simple stress elements, you should be able to draw more circle very, very quickly. This should take you no time. Bad Morse circle. Okay? What's the maximum shear stress in the material?
The average of the stresses?
Come again, please.
The average of the two stresses?
The average of the two stresses. The average of the two stresses will be that. Is that what you mean?
No, that,
I didn't think so.
minus
Okay, then say it again.
the average of the two stresses minus the smaller stress, minus sigma B.
Why not? Do you want to say radius of Mohr circle?
Sure.
Okay. So that's the difference between the 2 divided by 2, isn't it?
Oh yeah, that's
Difference between the 2 divided by 2. Does everybody agree? Okay, that's the maximum shear stress. Okay. One thing you need to get out of is the habit to think two-dimensionally. There's nothing wrong with what you said, by the way. That is the maximum in-plane shear stress.
sigma A.
There you go. Think three-dimensionally. You don't have two principal stresses. You have three principal stresses. One of them just happens to be 0. So draw all three Mohr circles. And now you can find the magnitude of the maximum shear stress. And as you can see, in this case, sigma A over 2. Agreed? Now, what does the theory say? Failure will occur when that equals the maximum shear stress at yield in a tension test. What is the maximum shear stress at yield in a tension test? I'll put it over here. In this case, what's the maximum shear stress at yield? What is the, well, first let's find that out. What is this at yield? Equal to what? This stress. When this part starts to yield, what is the normal stress that is acting on it? Can't be that difficult of a question. When does a part yield? It's right here. When its stress reaches the value at yield in a simple tension test. Isn't this therefore equal to Sy at that instant? The stress on the part is equal to the yield strength of the material. Does everybody understand that? Okay. What's the maximum shear stress when this happens? In this case, tau max equals what? Draw more circle. Now 2 of your principal stresses are 0. The other one is SY. Therefore, the maximum shear stress is SY over 2. Is everybody following that? So, here's my maximum shear stress. There's the shear stress at yield. We say yielding or failure will occur when these two are equal. In other words, sigma A over 2 is equal to SY over 2, which gives you exactly the same results as the maximum normal stress. It says whenever sigma A, which is the larger of the two principal stresses, reaches the yield strength of the material, it will have yielded. Okay. So, if the two stresses are positive, this remains exactly as is in the maximum normal stress theory. So let's draw the maximum shear stress theory in red. That's that part. This one for sigma A greater than sigma B, that for sigma B greater than sigma A. Everybody okay with that? Yes? Okay. The same thing is true on this side, where both of them are negative. Then the one that has the larger magnitude reaches the yield strength in compression first, whichever it may be, sigma A or sigma B. So these two remain the same. Does everybody understand that this will be the case? And if you have any questions, please go ahead and ask. I'll show you that that is the case if they're both negative. The one that has the larger magnitude reaches the yield strength in compression first. And it could be either here or here. Now, let's put that in here too. The second case is this case. This is 0, sigma A, let's say, sigma B, like that. Both negative. Let me follow the same thing. Now, so let's say for sigma A less than 0 but greater than sigma B, we'll get the same thing. In this case, sigma B over 2 is equal to SY over 2. Remember, the magnitude of sigma B is larger than sigma A, magnitude. Sigma B is smaller than sigma A, but its magnitude is larger. So, we get that. And if you flip the two, you get the other of the two straight lines. Now, this case. This case. In this case, your more circles will look like this. And there's your third principal stress. Now the maximum shear stress is the radius of the largest Mohr circle. And yielding will occur when that equals Sy over 2. So yielding will occur when the difference between the two principal stresses, and remember one is positive, one is negative. So when we say the difference, the magnitudes actually add, is equal to the yield strength of the material. Very similar to this, which I have now erased, very similar to that, which can be written as sigma A equals Sy. That shows when failure occurs. Locus of all points where failure occurs. Sigma A equals Sy, and that's how we drew this line, for example, this straight line. Sigma A equals Sy. I'm not differentiating between tension and compression here, because in most ductile materials, the two are the same. The yield strength in tension and compression in ductile materials, usually the same. There are some exceptions. Similar to that, where we drew those lines, we draw this line. This is the locus, failure locus. How do we draw it? Well, it's just like an xy coordinate system. X minus y equals 5. You draw the line. Assume sigma b is equal to 0, sigma a equals Sy. So that gives you this point. Now assume sigma a is equal to 0, sigma b equals minus Sy. Gives you that point. And that certainly is an equation of the straight line. That's your straight line. Very similar to this, you can flip sigma A and sigma B insofar as positive and negative is concerned and get that. So what you see in red is the area that the maximum shear stress theory predicts as the safe area. It says if your point falls in this area, then there is safety. If it falls outside of that area, then you have failure. How do you find factor of safety? Exactly the same as before. For example, of course, these two quadrants are the same as the maximum normal stress, but if you plot your point here, all you do is connect from the origin to that point and continue until it crosses this line. The factor of safety, therefore, is OC over OA. So we have two curves, or straight lines in this case. Load line, that's along which stress is being increased. Strength line, limiting value of the stresses. Whenever they cross, start of failure. The ratio of increase of stresses before you get there, factor of safety. No different than what we had before. But of course, the numbers will be a little bit different. Any questions? That's the maximum shear stress theory of failure. And it agrees with experimental results a lot better than the maximum normal stress. In fact, maximum normal stress fails you here. It says this area is safe, where that area is not safe. So we use the maximum shear stress theory for all of our failure analysis problem to see when a material will have failed. Any questions? Okay, next. And this also is used for ductile materials as well. I guess I'll leave that one there. I'll erase the maximum normal stress. I'll just use this. Maximum distortion energy theory of failure. This failure theory is based on not the stresses that are applied, although it relates to the stresses, but it's not directly based on the stresses. But it is based on the amount of energy that is stored in the material due to those stresses. Before I write the theory, let's take a look at the definition of this energy. Let's say you apply a load P to this rod, and the rod elongates a distance E under that force P, and by doing so you will have done work on that rod. How much? How much work have you done? Definition of work. Okay, so let's say I weigh 150 pounds and I just walked about 10 feet. How much work did I do? There is a force, right? 150 pounds, my weight, and there is a distance, 10 feet. So I did 1,500 foot-pounds of work. Do I look like I did 1,500 foot-pounds of work? I don't think so. So get that out of your head. It's not force times distance. Or at least qualify it. If the force is a constant, no, that's a first requirement. The force has to be a constant. If the force is a constant, and if the displacement is in the direction of the force, then yes, it is P times that displacement. But only if the force is a constant, and only if the force is in the direction of the displacement of that force. In my case, the force is vertical, the displacement is horizontal. They have no components in either one of the two directions. Force doesn't have a component in the horizontal direction. Deflection or displacement doesn't have a component in the vertical direction. So I basically did no work. And I look like I did no work. So it's not force times distance. It is the work done is that. It's the integral of P times the increment of displacement of P integrated from 0 to whatever distance you have applied the force. In this case, is the force P a constant? Remember, we're doing a tension test. When you did a tension test, did you do it with a constant force? Was the force applied to the specimen a constant? Yes? So you started with the yield strength of the material? No, you started with 0. Force was not a constant. You started with 0 force, then you increased it a little bit, then you increased it a little. That's how you got your points and drew the stress-strain diagram. Force is not a constant. In fact, if we draw force versus displacement for something like this, which actually mimics a spring, that's what we get. Assuming that the behavior is linearly elastic. And if this is E, that's the work done by the material. So it's not P times E, but it is, in this case, because of the linearity, PE over 2. So you've done this much work on this rod. And you know that anytime you do work on a system or an object, you increase the energy of that system or object. Did we increase the gravitational potential energy of this rod? Not if we don't move it up and down, and that has nothing to do with the applied force. Kinetic energy? There is no kinetic energy. This has 0 velocity, still has 0 velocity. So what did we increase? Where did the work go? You guys do study strain energy in 219, do you not? Did you study strain energy in 219? Or did you not study strain energy in 219? Anybody heard of Castigliano's theorem? When you studied energy. The work that you do goes into the increase of the internal energy of the material called strain energy. This is the energy that is stored in the material by stretching the bonds that exist between its atoms. It's called strain energy. So when you did this work, you increased the strain energy in the material. We talk about not the total strain energy, but about strain energy density. So let me define that here. Strain energy density is equal to strain energy per unit volume. So, if we did this much work on the rod, we increased its strain energy by that much. Therefore, the strain energy density in this case can be found by saying that the total energy put into the material divided by, actually let me rewrite write it as U over V and then that. U divided by volume. That'll give you the strain energy density. U is PE over 2. Volume, assuming that the length and the cross-sectional area remain or are constants, is that. Then P divided by A will give you the stress. E divided by L will give you the strain. So this is equal to sigma epsilon over 2. This is assuming linear elastic behavior of the material. Stress and strain are related linearly. This is called strain energy density. We say that according to the maximum distortion energy theory, when maximum distortion energy density in the material, when, I should say, write a when here, when maximum strain energy density at any point in the material, at any point in the material reaches that at yield in a simple tension test, the material, oh, in a simple tension test at, did I say at yield? Yeah. The material will have yielded. So what do we mean by this distortion business? We say the strain energy that goes into the material is divided into two parts. One part produces only shape change, no distortion. In other words, if the shape of the material to begin with is a cube, it will remain as a cube, no angle change. Shear stress, as you know, however, changes angles. And that's really the one we're interested in, because that's what causes yielding. So we divide the strain energy into two parts. One, solely due to volume change. The other, solely due to shape change. In other words, the cube doesn't remain a cube. Let me give you an example of when we have just volume change and no distortion. A hydrostatic state of stress. In other words, you have a little cube, you take it down to the bottom of the ocean. What will be the shape of that cube at the bottom of the ocean? A cube. It will be a smaller cube, but it will be a cube. There will be no change in its angles. All angles will remain 90 degrees. The pressure is the same all around, which is the same stress that we have shown here. So here we say whatever energy you put in here went into volume change. If, on the other hand, there are changes of angle or shape, we say that the strain energy that's gone in there produced a shape change, distortion. That is the one we're looking for. So take a quick look at a couple of these slides and we'll have the quiz. This one is actually maximum shear stress that I drew for you on the board is still on the board. And what I talked about regarding the factors of safety. And so next time what we're going to do is take this, divide it into two parts. One producing only volume change, the other one producing only shape change. And why they are as you see them on the board, I'll talk about that next time. Any questions? Okay, please put away everything except your books, your pencils, and your calculator.